Hello, everyone. Thank you for joining us again. I'm Philip Johnson, the Executive Director of the Oregon Shores Conservation Coalition. Oregon Shores is celebrating its 50th anniversary this year. We've spent the year hosting a series of talks, not looking backward, but looking at the next 50 years, at the issues we will be confronting, such as tonight's talk on the future of the shoreline. Oregon Shores, if you don't know us, is a comprehensive regional conservation group, by which I mean we potentially address the full range of conservation concerns in our region, anything from land use planning, water quality, to shoreline management, marine conservation, endangered species. And we often work with our members and other coastal citizens to assist people that are willing to get involved in regulatory processes, whether that's land use planning or others. We are perhaps best known for our Coast Watch program, through which volunteers adopt 1 mile segments of the shoreline and keep watch for a wide range of phenomena. We can always use additional eyes on the beach. If you'd be interested in helping us protect this coastal region for this year and the next decades to come, I hope you'll visit us at oregonshores.org and learn more about us, and perhaps consider adopting a Coast Watch mile. As a quick commercial break, 2 ways to assist our work right now are through the end of the year, but it's a rolling auction, so new items are being added and things come up for bid at different times. In fact, a couple of items are coming up for bid on Friday. And then there's our mile by mile competition, a friendly competition through which donors designate a mile of our shoreline. It's sort of a popularity contest. And at the end of the year, the mile that has garnered the most dollars and the mile that has been selected by the most donors will both win. And those donors will receive a treat, which we're keeping under wraps at the moment. You learn about both of those opportunities, again, on the oregonshores.org website. There are little buttons for both right at the top. So again, we're the Oregon Shores Conservation Coalition. And while we deal with the entire coastal region, from the crest of the coastal mountains to the edge of the continental shelf, the heart of our work and our focus has always been our public shoreline, public beaches here in Oregon. I'm sure everyone who's joined us tonight loves the shoreline and the way it is sculpted and endlessly changing as with the collision of waves and sand. So a book that's titled Waves and Beaches would speak just directly to what we most love. Those of us of a certain age, or younger people that discovered it in a used bookstore or the library, often have had our fascination with the shoreline fed by the book Waves and Beaches, written by Willard Bascom back in 1963. So it has tutored several generations on the nature of the shoreline. It's still considered a classic, but a lot has changed in the last 60 years. So Kim's
There's the original one.
the cover there. A lot has changed in the last 60 years. As our speaker tonight says, the waves and beaches have elevated their age-old battle, literally in the age of sea level rise due to climate change. Kim McCoy was actually mentored by Willard Bascom early in his career and toward the end of Bascom's. So he's kind of carrying the torch. And as he says, his last homework from Willard Bascom was updating his book, creating a 3rd edition of Waves and Beaches with the subtitle, The Powerful Dynamics of Sea and Coast. The new edition preserves much of what Willard Bascom did, but substantially expands and updates it. It both opens out into our current era of climate change, sea level rise, and dramatic change in the shore. And also, whereas the original Waves and Beaches was more North America centric, it also opens out to a more global perspective. Kim McCoy is a physical oceanographer and also an adventurer who in his career has lived in 7 countries, has studied waves and beaches and other phenomena on all 7 continents, has sailed the 7 seas, so to speak. In his scientific work, he particularly has focused on coastal wave dynamics and latterly on the effect of climate change on coasts around the world. He's an expert in instrumentation for studying the ocean and has patents on a number of different instruments. I won't, recount his very lengthy and diverse resume, but I'll just note a couple of things: that he was the principal scientist for NATO in Italy for a time. He's also the CEO of Ocean Sensors Incorporated, which used some of those instruments. For all his global wandering, though, Kim McCoy was born in Boise, and it tells me he has relatives all over the Northwest and is quite familiar with our Oregon coast. So in effect, I am welcoming him back to the Oregon coast, digitally speaking. And with that, Kim, it's all yours.
All right. Well, thank you, Philip. And thank you to Oregon Shores, your whole team, for having me this evening. So let's see if we can do this here. I'll start sharing the screen. This presentation, let's see, I'm going to continue. This presentation is really an update of the first and second editions of Willard Bascom's Waves and Beaches. And is that all right there, Philip? Can you see that fine? I assume it's okay. And it's a big look at the Earth, but I'm trying to focus on the coastal wave dynamics aspects of it. And in the 21st century, it's really difficult to actually just home in on anything that is just coastal without looking at many other things. So I'll start off now. It'll go a little bit fast in some areas, but we'll try and cover the coastal aspects, a little bit of Oregon shores, and also how the watersheds are affecting global sediment discharges. So let's see here. I am not, there we go. Okay, so there's a Columbia River watershed. You can't really look at sediments without looking at watersheds. And if you can see here, this is Canada, this is Idaho, reaches all the way into the Columbia River mouth near Astoria. And everything that happens upstream in this watershed affects what happens here in the coast. So as much as it would be very nice to be myopic about just looking at the discharge of the river there, it's unfortunately intimately connected with what happens upstream. And it's not just the Columbia River, it's a global issue. So here's a quick list of the estuaries along the Oregon shoreline. And it starts up here at the Columbia River, innumerable estuaries along the coast. The estuary is where you have exchange of water in and out of the land during high tide and low tide, where you get salt water and fresh water mixing. And so it's impossible in the short period of time to actually cover them all. And I'll probably only cover about one or two of them. So here's the Columbia River, Astoria, and massive discharge there. Now you see here, this is the bathymetry, so how deep it is here. It shows you it's very deep here. So these sediments are, although you only see the flat water, it's very complex below the surface of the water. And so the bridge goes across right about there. So you have a shipping channel over here, but if you have a big change in the watershed, you'll get a change in all these channels, and that can be episodic. So we're having a change in weather patterns. So what happens upstream in that watershed could very easily push out millions of tons of sediments and change the Astoria bar, the Columbia River bar, which is infamous for mariners. So let's try and do a little bit of view from Oregon, but this is going to rapidly get off into the rest of the world because it's all the same. So how did I get here? This vehicle over here on the left is called a duck, D-U-K-W, and a fellow by the name of Willard Bascom, this is the fellow right here, who wrote the first two editions of Waves and Beaches. Willard Bascom was hired in Astoria in 1946 by John Isaacs. That's where they met. Willard Bascom was an mining engineer. He went to Colorado School of Mines, and he was hired for the Waves project. And they wanted to know what was happening. Amphibious landings had been very numerous during World War II. And so the government says, well, okay, we don't really know what's happening here. So why don't we go and study them? So they went, they took this duck, they had 3 of them, I think, and they go along the surf, and someone on the shore would measure an angle. Person on board would drop a lead line to see how deep it is, and then they'd run along this range pole. That's how they did it then, much more modern now. And here's a picture of Bascom. This is Bascom's head. That's about a 12-foot breaker in Carmel, California in 1947. So little did I know that I had something very in common with Willard Bascom. I met him in the late 90s. I'd used his book a decade or 2 decades before in graduate school. But Bascom, when he lived on the Monterey Peninsula, he met John Steinbeck, and he also knew Doc Ricketts between the Pacific shores. And I happened to have spent several years on the Monterey Peninsula, wandering around Cannery Row and reading Steinbeck's novels. And little did I know that one day I'd be heavily interacting with Willard Bascom, who was buddies with these guys. And Bascom knew a lot of people. So here's Willard. It's in a deep sea drilling project. There are four people here. This is Walter Monk. These people are unfortunately all deceased. Walter Monk, known as the Einstein of the oceans. This is Gustav Arrhenius, Willard Bascom, and this is Roger Revelle, one of the founders of University of California, San Diego. And I was lucky to have known all 4 of those people. And they were instrumental in oceanography after World War II. Actually, Roger Revelle started before. And that's what generated Waves and Beaches, the first 2 editions by Willard Bascom. That's how I got here. And last summer, I took a trip up the coast and stopped in Astoria, and I met with Oregon Shore's wonderful person, Jessie, and provided her with a copy of Waves and Beaches. And this photograph is to show that it's a complete loop. Where Willard Bascom started studying waves was in Astoria, and there it was, a book being returned to Astoria 75 years later. Okay, water starts at high altitudes, rains, might be snow melt, might be rains from rivers. Here's an alpine excursion. This Mount Whitney in the distance. This is alpine water that flows down hundreds of miles, even thousands of miles. This is Neumayer Channel in Antarctica. Ice is melting there. Here you can see it sheared off, that blue ice. Here's blue ice, it's shearing off. The Earth is warming. So when things melt above water, above sea level, that raises the sea level. When it's sea ice, it doesn't. So what's important is what's happening above ground, above sea level, and it's melting everywhere. And sometimes you have brash ice, and so you can have ice pounding up against the Earth, creating small grains of sand chipping away at it. Sometimes you can have stuff like this, and it looks like it's ice, but actually this is salt in the Dead Sea, but it's protecting the rocks as they get ground into sand. So as the Earth warms, ice not only melts and fractures, but it also melts from below because the water is warming. So although we have lots of satellite images of what the ice cover is, we have very poor knowledge of how thick it is. Just as a note, yesterday, I think it was, an oceanographer, Klaus Hasselmann, who I actually know in passing, received the Nobel Prize. First time an oceanographer has ever received a Nobel Prize was yesterday. Anyway, he was involved in the climate change, global warming studies. So this is a lecture given by Professor Ferrari from MIT, and it's a little bit technical, but very important. The ocean is the key component to climate change. And the ocean is turbulent. I show these things mixing. Macro turbulence, that's so large scale stuff, affects climate on the decadal timescale in the periods of tens of years. Whereas micro turbulence is stuff that's very small in length scale, affect climate on the centennial timescales, things that take 100 years or more to change. So things are changing at all length scales, but we don't really know the repercussions of these small scale fluctuations. So turbulence is everywhere in the universe. So many of you have probably heard of the polar vortex. And this is basically winds and I'll call it atmospheric conditions that circle the northern hemisphere. There's a similar one in the southern hemisphere. When you have a strong gradient across here, then things are stabilized. It's like having oil and water. The oil stays on, the oil is lighter, so it stays on top. Well, when you have the differences between the layers be less, they become unstable and they start to fluctuate. So this summer we had really cold period in Texas, and we had really hot weather up in Oregon where you are. That's because this meandering of the jet stream, also referred to as a polar vortex. So the warming Earth is causing these rapid fluctuations in our weather patterns. I think everyone's seen that. So here's an animation from NASA. Starts in Northern Europe, comes across here down to North Africa, the Sahara. Watch this weather that comes off of the Sahara across the Atlantic into the Caribbean, north portion of South America, into the Caribbean. There's a tornado. This is all being generated from Africa, and it affects our weather. So you cannot differentiate, you cannot separate what's happening anywhere on Earth. So when things happen on a global scale, they affect us in the north, in the west, in the east, south. They're everywhere. It's all connected, all the way from Africa in that little video. So there are different types of waves. I'm going to go into waves here in a moment. So this is a time scale. It's not linear. It goes seconds, minutes, hours, months, decades, centuries, and millennia. Here is a change in sea level. So these are different types of waves and how they change sea level. Little tiny capillary waves. I'll show you one in a little while. Ripple. These things only change in the centimeters. So just very small length scale, just an inch or two. And then you have chop that can get up into 2 or 3 feet. Then you have seas that can get up 4 or 5 feet. Then you have swell that can be up to 20 meters. That's 60 feet, over 60 feet. You have this surf beat. That's an interaction of waves, and some waves come together and they make them high for a little bit. Surfers sort of talk about the 7th wave. It has to do with this beat frequency of waves. And those things can change in some areas over 15 feet. Now we have 3 things in orange here in red. A tsunami, of course, an impulsively generated wave. I'll show you in a second. Storm surges, which are from weather patterns. Those can change over 40 feet. You can have a storm surge. And then you have tides in this area, and then you have global climate. So you can see things that are very short scale happen very fast. So short in distance happen very fast, and things that have very large effects take long periods of time. So you have El Niños, this 11-year sunspot cycle, and industrialization. This is a question mark. We don't really know how big this blurb and sea level rise will get. And then we have these unusual things, well, not unusual, most people just don't care about them. They're called Milankovitch cycles, and they have to do with the orbital periods and eccentricities of the Earth around the sun, and they vary in 20, 40, and 100,000 year periods, and sometimes they overlap and sometimes they don't. So here's a polar projection. So here's Greenland, here's Europe, here's North America. You're right over here somewhere. And this is an image of permafrost. So there's the dark area is constant permafrost, but this thawing permafrost is moving further north, which is causing massive changes in the coastal regions. So when you talk about erosion from the, let's say, from the Mackenzie River, which is, I think, the 2nd largest river in North America, which empties into the Arctic Ocean, how permafrost is keeping the shoreline solid and how waves interact with the permafrost or lack thereof, or ice on the coastline, is extremely important. And as most people have heard, The ice cover is diminishing in the polar regions. And as that ice pulls back, the shoreline is no longer protected. And so the waves that used to hit ice first, I showed you a picture earlier, is now hitting the shore. So the erosion is greater because there is less ice cover. Now, what happens? Well, okay, theoretically, and also measurements have been made about the rise. Well, we extrapolate, we say if there's a 2 degrees centigrade, that's about 3 degrees Fahrenheit raise in global temperatures, this is what's going to happen to sea level in Florida. So all this blue area will be underwater. Here's Miami down here, you know, that's long gone. The coastal region here, Orlando has some coastal flooding, St. Petersburg. So it's not a pretty picture. Most of you have heard about those things, but that's just a 3 degree Fahrenheit rise, 2 degrees centigrade. And it's global. This picture of Jakarta, Indonesia. So mild is, I think this is a 2 meter rise, and this is a 3 meter rise. No, sorry, this is a 5 meter rise in the dark blue. So you've got 5 million population in Jakarta, Indonesia. What are the Indonesians doing? They're actually planning to relocate their capital, Jakarta, because it's just become too expensive. They built over 20 kilometers. It's about 12 miles of barriers, but the sea level is rising too fast. And that's complicated because they're extracting fresh water, and the land sinks because now there's less water underneath. And so the land is sinking, sea level's rising. It's not a pretty picture. So let's look at waves. These are on the left here. These are capillary waves. These little tiny things. They're only about this long. They're very, very short. So less than an inch. From here to here is less than an inch. And this wave is propagating in this direction. And so on a larger scale, if you drop something into the water, this is familiar to everyone, you get waves, and that waves radiate outward. And each wave, when it strikes the shore, gets rid of its energy. So this is a picture of the turbulence taken underwater. This happens to be in Greece. So here you can see the sediment being resuspended. So every time a wave comes into the shore, it resuspends some sediment. Usually you don't see it because you're above water, or you got your eyes closed. But every single wave is moving particles of millions of grains of sand. So, you know, waves can be fun. This is a tidal bore in the Severn River, which is in Great Britain between Wales and England. And these things happen a few times each year. And so they're fairly well predicted, but you can see that surfers are definitely enjoying these things. It's a free ride for a couple of miles. And sometimes the waves, when they come in, they come into a steep beach, they'll reflect back. And here's a picture of a reflected wave. Here's another one. Surfers are doing well. Here you can see they didn't quite expect, here's a wave that has just gone back in. So it's jacking this wave up. You can actually see the wave returning back out to the sea here. And this one right here is the one that's coming into shore. So how do waves get created? So the wind generically makes waves, and the faster the wind blows, the bigger the waves can get. You need a greater the distance over which the wind blows, and the longer period of time, the stronger wind, the larger the waves can get. Another type of wave is a tsunami, and that can be created by, this is a picture of an underwater earthquake. Suddenly it shifts upward. You know, we've had 2011, we had the tsunami that struck Fukushima that changed how people do things, power and everything. So this was an ocean wave generated by an earthquake. So you can also have waves generated by storms. Now, this may be a little hard to see for some, but this is Texas here. This is like Corpus Christi down here somewhere. This is the Gulf of Mexico. So you have this weather pattern that pushes in. So you're going to have massive amount of energy pushing in from the Gulf of Mexico. You saw that video before coming across from Africa, and all that energy is working its way towards the west, turbulence working around, and it hits the right temperature water, creates storms, and creates big waves. So a little bit of wave terminology, forget the equations over here, but there's 3/4 types of major waves. Spilling, when you have a very shallow, not a very steep beach. Plunging, when it gets a little bit steeper. And then collapsing when it's really steep. You see that in Tahiti, the surfers love that there. And surging when it's really, really steep. It's so steep that the wave actually comes in, it doesn't even have a chance to break, just surges up the front of the beach. This is, every wave has what's called an orbital wave velocity, little circle. And at the surface, it's a circle. And as you get deeper, it sort of turns into an ellipse and diminishes with depth. So this is the wavelength. Once you get 1/2 the wavelength, so that's from here to here, once you get that distance down, the motion on the bottom is negligible. It's not zero, but it's negligible. So it's not moving sediments around. So most of the motion in wind waves is at the surface. Now, tsunami's energy can actually goes from the surface all the way to the bottom. You don't see it at sea, but when it reaches shallow water, basically all that energy compresses. In essence, it doesn't compress, it just doesn't have anywhere to go. So it rears its head as a wave. So here's a little bit of nomenclature. So it's a coastal area. You have a beach going from this line here to this line here, the foreshore. This is the shoreline. Here's a surf zone. So our changing shores, really, how does all this change? And here we have a berm. Here's a berm and here's a bar. And these migrate back and forth depending on the waves. So what you measure one week is not necessarily what you're going to have the next week. So you might have the berm cut back, pile up on a bar, and cause the waves to break further out. So this is and of course, the tide modulates, so it makes it all fluctuate going up and down. So as a high tide's there, it'll be here. Low tides, it's going to be down there. So it's all changing there's no one instant that's repeated in time. Every wave is unique. And then when you get in the coastal zone, and you have a lot of sediment, this is the Chesapeake Bay over here, you have a lot of sediments in the watershed pushing out. On the Oregon coast, you also have a lot of water coming out through the rivers on the northwest coast. And they have an overabundance of sediments, and that creates these barrier islands. Now, those barrier islands protect the mainland. You have a big storm, or if people have been allowed to build on the barrier islands, then those can be destroyed and people can lose their homes. And very unusual beach morphology, beach shapes come up. These are cusps from the southern coast of England. And this distance here from here to here is about 35 feet. And then humans have built dams. So over here you see just a earthen dam, and some dams let sediment go through and other dams do not. So sediments in the watershed coming down the watershed then affect the coastal zone. So here's the Mississippi River Delta, and this is no different than most other deltas in the Gulf Coast or in low-lying areas such as the Netherlands or the Carolinas. And here you see 1 through 6. So the very first one was deposited around 5,000 years ago, 4,500. And the most recent one has been active for the last about 500 years. So depending on what's coming down the Mississippi River, you get a big pulse of energy, sediment coming out. Well, it might cut a new river path. And so it'll go over here, go over there. And you can see over the last 5,000 years, it's meandered quite a bit. And those sediments tell their story. So big sediments, large diameter sediments takes lots of water to move large grains. And this fine sediments periods where you don't have too much water flowing. So big water, little water, big water, little water, big, little, big, little. Our history is in the sediments. And then in a shorter term, this is only about a foot high right here. There's a person way back there. And each one of these strata stratum is basically one wave. It's washed up the shore at the end of the swash, and then it's come down. So each one of these is a little record, but this probably hasn't been formed in more than about maybe a week, maybe even a day, depending on whether or not the berm is building up or whether or not it's eroding. So in a headland and a embayment, you have the headland, you get concentration of wave energy and it erodes the headland. In the embayment, it spreads out, so you have less energy per unit beach. And then after a few hundred years or so, the headlands cut back, you get spits forming or bars forming, and it starts to fill in. So here's a picture of one of these. So here's a water flow. There's a bunch of sediment coming from somewhere. And this channel is being cut by the sea, well, by the river into the sea. So all these sediments are relatively new, but those could disappear in one big storm, or they might be there in 1,000 years. And in that river, so the river discharge, the fresh water goes out into the seawater. And as a tide rises, it reverses and goes back upstream. So when the tide reverses, the salt water goes into the estuary. And when the tide is low, it goes out. So this is Liz Unbrat. I've never met her. She's a geomorphologist. And this is a little vignette here of how small changes in sediment can make a big change in the geomorphology. So how we see estuaries in coastal regions. And so every estuary along the Oregon shore is affected by these changes. So mud in estuaries, I don't know how much of that you can see, but mud in estuaries. So let me, this says, I'm not sure if you can see, this says only sand. This says small mud supply, large mud supply. So I'm gonna just, I hope that's showing it better. Philip, if you can give me feedback, or Rena, on that one. So here we see only sand gives a different delta. Small amount of mud gives a different type of delta. And a large mud supply gives different. You can see here in each one of these middle sections, you have a different shape of the channel. And that's only by changing the type of sediment. And the way they did these experiments are really clever. So this thing is really long. It's probably about 60 feet long. And this whole table rocks back and forth to pretend like the tide is rising or falling. And so you get water going in and out this channel. So that's how they do these experiments. Pretty amazing, very clever way of doing it. And so by changing the different types of sediments, you can see how the different portions in the delta form are upstream. So this is a river mouth. You can see when there's lots of flow, it'll cut back. The tide will come back in. So it's always constantly churning the sediments. And here, this is Carmel River mouth in Carmel, California. Here you see a newly created berm. There's a river mouth here. Large waves push it up. You can see it's pushing up the end of the swash here. And the big waves, there must have been just a wave right here because it's still wet, reforming the top of this berm. And sometimes it's hard. This is granitic rock. It's being pounded rock against rock, making these smaller pieces of sand. And sometimes even smaller scale, these are limpets. These are probably only about an inch, inch and a half in diameter. And they sit there with their what's called a radula. They grind away trying to get the algae that's on the rocks to eat. And sometimes things don't erode. This house has been there for 60 years, no problem. So if you're on a rocky headland, you've probably got a good chance, unless you're going to have a tsunami. And other things are much more dynamic. This is Point Sur and Big Sur area. This is a detail there. If we got a big rain, this would cut through here. Now, sometimes humans want to build in these areas, if it's been stable for 10 or 20 years. Other areas, like in Antarctica, you have these really, really fine sediments that come out from the ice grinding away on the stone. And sometimes the sand just goes out to sea in the winter, sorry, and the small summer waves work its way back. So this change probably it's probably 8 feet of sand in one season. Sometimes the shores are protected by kelp. About 40% of the temperate coastline is protected by kelp. Large kelp, that's in New Zealand. That's a massive chunk of kelp. Sometimes the shoreline is not protected at all. This is in the southern coast of England. These are cutting back. I walked across this to take this photograph. This has since collapsed. So it was an archway that was up like this. So some shores are really getting inundated. Now we'll go to the Bayocean Park. Some of you listening might know of this. This is on the opening of Tillamook Bay. So here's Tillamook down here. Here's Garibaldi. Here's the opening, and this is Cape Meares. So this changed in time. So here's a picture of 1947. They had just built the jetty a couple of decades back, and it changed the whole shape of this area here. Unfortunately, they had started in the early part of the 1900s selling property, and people had built a bunch of houses, and over the period of about 50 years, things were built and they completely disappeared. They built a second jetty, the south jetty, and the sand started to come back. Here's a chart. So here's a second, this is the southern jetty, and all this has all come back. It had all cut back. It cut all the way through here in the 30s and 40s, and all the houses, all the structures had fallen into the sea. There's a very nice documentary if you search on the history of Bayocean. It's a human folly. Sometimes things change without humans interacting. So this is Cape Hatteras on the East Coast. Here it is in the 1850s, 1912. So it's cutting back here, but it's forming here. So if you had a house out here in the 1800s, you'd be unhappy. But if you had a house here, you'd be happy. So because you're getting more land. So sometimes the sediments are just shifting in one direction. So if you happen to be in the right position, you gain property, otherwise you lose it. So this is a bar at low tide. And so here's a bar, and there's a channel, it's cut. And this can change in a day. Big storm, completely change it. This is another type of influence right out here. This is La Jolla Canyon in San Diego, La Jolla. And it's a submarine canyon. So it affects the waves. You can see these curved around here. That's because it gets really deep here. And there's actually a little channel. So you can have submarine canyons that affect how waves propagate. Every single wave, like I showed you before in the detail, stirs up a bunch of sediment. That sediment goes places. Sometimes if the wind blows, it's blown ashore with the help of seagrasses. And here's a detail of seagrass, a dune grass in the dunes. And when the wind blows in the picture from right to left, it's slowed down by the blades of grass. Some of the speed drops down, and some of the grains stop blowing, and it builds up the dune. So it's a small process. Some grains of sand, super fine. This is almost like flour, and other things are really coarse, like you see here. Now, this isn't really considered sand, it'd be cobbles, but nevertheless, it ends up being sand after it's ground up, and here you can see sand over here. And sometimes things slump. So remember, along the Oregon shore, you have all these things. So there's no one answer to what's happening to the Oregon shores. Sometimes it slumps down. This slump, I think, has been there since the 1920s. And here you can see it's slowly giving up its larger cobbles and rocks. Each bar, this was a big bar, and then the waves in the last high tide came over, and then it says, oh, okay, I'm going to go back out to sea. And it cuts through the bar, and that bar becomes 3 bars. And sometimes the headlands are there. This is a big chunk of hard rock, and the waves refract around here when the high tide is high, and it pounds against this. So probably in 10 or 20 years, this will be cut through, and this will just be an island. Some things hardly ever change. This picture of me in the south of Italy, probably in about 30 feet of water. And these blocks are blocks of marble that fell off of a Roman ship 2,000 years ago. So they've been sitting there for 2,000 years, haven't changed. So some things change on a daily basis, some things never change. Here's a little video. Let's see if this goes. This is about a year's worth. This is LiDAR, so light imaging. And you can see the slope just collapses there. I'll let it run a few times. And then the US Geological Survey, Army Corps of Engineers comes back and rebuilds it all. So sometimes they're massive slides, sometimes they're little tiny slides. So you never know what's going to happen. Earthquakes can cause it sometimes, or just simply a large rain can liquefy sediments and cause them to slide. Sometimes really subtle. So this is in the Arctic region. This is a dry riverbed. So because the weather patterns have changed, there's no water flowing down this riverbed. And what's happened is it's dry and the wind's blowing in this direction. And this is dust. This is a dust storm. And what happens is that dust settles on the ice. And now it's dark instead of light. And the sunlight coming down hits the dust and melts the ice more rapidly. So dust in the atmosphere has an incredibly important role in climate change. So droughts can cause an increase in temperatures, which can melt ice. So here's the Nile Delta in Egypt. So the Nile flows into the Mediterranean. And in the 60s, they built a dam up in Aswan, 500 miles to the south. And it changed the morphology, changed the shape of the coastal delta. And it also caused the fisheries to change. So humans intervene, all sorts of, here's some jetties, and you can see it got cut back here, and you can see a recent storm went completely over this coastal island, cut it back, and obviously they've stopped building here. I don't know if there were houses here before, but jetties can have a very, very adverse effect on the flow of sand and the flow of energy of waves. Sometimes things run ashore that you don't weren't designed to be on shores. It's an oil rig in Great Britain. And sometimes they're pristine. This is in New Zealand, where windblown sands have blown for probably centuries. And they build up these big dunes. These are most of these are sand dunes with vegetation on top. And this goes probably a mile inland. In some areas, nothing changes except for erosion. So this is in Vietnam. Here you see the tidal excursion. And this is dolomite. It's a type of soft rock. And the seawater has eroded this. So you can see that, and this took a couple thousand years because sea level hasn't changed very much in the last 4,000 years. It's starting to change. So if sea level changes, well, this will go up a little bit more and it'll cut back. This will probably fall down, but this is a very good example of a shoreline that hardly changed at all. But of course, there are lots of people living in the coastline. This picture in the Mekong Delta. People have their livelihoods in low-lying areas. You know, the coast of Oregon is basically not populated compared to many Southeast Asian cities. In between India and well, in the Ganges Brahmaputra Delta, Bangladesh and India share the largest estuary in the world, and there's about 50 million people that live on it. Sometimes things go wrong. This is a ship that's run aground with a bunch of containers. So now I'm getting into human folly. And this is a Rotterdam barrier here. This is part of the Delta Works in the Netherlands. These articulate this, the ocean side here, the sea. And when there's a storm surge, it comes in, they float these things that this one rotates this way, this one rotates in here. And this is gigantic. This is over 1,000 feet across. And they stop the storm surge. And they've done it a couple times very successfully. The thing cost about $500 million roughly. And the damage that it keeps from happening is in the many billions. So it's a very cost-effective method of protecting harbor areas that are important for commerce. Once again, the weather is a global issue. It's changing. Remember this summer during the Olympic trials up in Oregon, there was a terrible hot period in the Northwest. It's, we don't think about it. Here's Florida, but the ocean experiences heat waves and cold periods also. And that affects how the ocean is heating or cooling, how the organisms in the ocean are thriving or dying. So this little busy graph here, this axis here is time. This is 20,000 years. And follow the blue line. The blue line is a change in sea level. So over the last 20,000 years, sea level has changed 120 meters. That's 400 feet. As I mentioned earlier, it's been pretty stable the last 4,000 years, but that's changing. So this red line is a rate of change of sea level. So this is in distance per 1,000 years. So this means it's hardly changing at all in this period here, but this is now ticking up. It's starting to change very rapidly. So we, as scientists, we have our eyes on those sorts of things, have for decades, and we shouldn't ignore it. The data is clear. So one thing that happens in coastal areas is very subtle, is saltwater intrusion. When water is pumped up, and there's not enough fresh water replacing it, because either jetties or diminished rain or too large a population of pumping too much fresh water out, what happens is salt water comes in underneath the land. And now the fresh water that was pumped out is now salty, in some cases too salty for drinking and too salty for crops. It's a massive problem happening around the world. In areas where you have granite and stuff like that, it's less significant, but in low-lying areas, certainly in estuaries and coral areas, it's very important. And people are making measurements. Scientists, there are a lot fewer scientists than there are people going to the beach. This is at Scripps Institution of Oceanography. This is Andrea Ogston's gizmo at University of Washington, studying the Elwha River Delta. Sometimes things happen rapidly. So this is a coastal island, barrier island, on the 6th of September, 2014. Just, 5 weeks later, bam, it's gone. The whole coastline has changed. This barrier island has changed. Things can be there for decades, nothing, then you get a big rain, it pushes through. So if the dune is compromised, if people are using it, running trucks and stuff over the dunes are basically like a bank account for the berm. And if you keep making withdrawals, if you will, from the dunes, the coastal islands will suffer. So this project I was on, California beach vanishes, but scientists get their data. Yeah, it's not easy working the surf zone. This is the Elwha Delta on the Strait of Juan de Fuca. They took out a couple dams on the Elwha River. This is a brand new delta. I think they took the last dam out in 2015 or 16. So this is all new sediment, all new things that are coming down the river. I ran along this thing. It was a very wonderful feeling. It was like a child running in for the first time. It just felt differently. Sometimes things run ashore that aren't intended. Like I mentioned before, this is off the coast of Namibia, Skeleton Coast. This beach runs for several hundred miles. Largest sand dunes in the world are in that area. But it's happening everywhere. This is a coastal, it's a tropical, so South Pacific atoll. And the direction of the waves are changing. So weather patterns are changing and the directions are changing. And you have these, what's called spur and groove alignments. They're basically like fingers. So a deep portion, a high portion, a deep portion, a high portion. And that runs up and over the coral reef and into the lagoon, and it makes a circulation pattern. And that's changing. So with sea level rise, you have like a triple whammy. You have the wave directions are changing, sea levels rising, and also you have saltwater intrusion because that water is going up over onto the land now, and it's seeping into the ground. So one very poorly studied thing is what happens to a storm surge when it goes up over the land. It's all salt water when it comes from the sea. So it percolates down and it spoils the aquifer. This is San Diego Bay. This is hard land. This is a sand spit, basically. It's North Island military base. And there's a water source up here, river, small river, and it comes down this way and this way. And it used to go back and forth. It would meander back and forth. And it doesn't do that anymore. But one big storm and one day it might. So coastal things are built everywhere. This is an estuary. You can see the tide, well, a wave on top of the tide coming in. Unfortunately, from this point all the way to there is they've built up a roadway, and there's no way for the water to pass back and forth there. So what happens is water comes through here really fast. It pushes a lot of sediment into the estuary. And then as the tide drops, the speed at the mouth is still high, but back where the sediment's been deposited isn't high enough to bring the sediment back out. So what happens is this estuary keeps filling in, and that's what's happened all over the world. This is a river mouth. This is in Oregon. Here's a surfer. Changing patterns, rain patterns way up in the watershed will change the bar formation here. So you really can't separate, as I said early on, you can't separate the watershed from what's happening at the coast. You have things happening in the polar regions. This is in Antarctica. This has been calved. The rate of calving is higher, so calving of icebergs. This is about 80 feet high, and these things will continue as long as the climate keeps changing. Coastal things will be inundated. This is at La Jolla Shores in San Diego. This was only built a few years ago, already inundated. Sometimes you have too much sand. So this is in Arcachon in the Bordeaux region of France. Here, it's the largest sand dunes in Europe, actually. And here you can see there's just too much. So as I mentioned before, you can have deposition or you can have erosion. This is in the Gulf of Mexico, Mississippi River Delta. The prior building was not so high, it got swept away, so they built it this time. Now this is in Villefranche in southern France. This is oceanographic research facility here. This harbor, boat harbor, small portion of it, was built by the Romans. It's been there for 2,000 years because sea level hasn't changed very much here. So some things are in the right place at the right time, being last 1,000 years with not very many subsidences or water pumping and changes in the ground level. But globally, we have sea level rise. So could very well be that in a century, this is no longer usable after 2,000 years. This in Malta, these fortifications were built about 500 years ago. Massive harbor facilities all around the world. These harbor facilities are being challenged by sea level rise. Now, these are in Chile. There was a tsunami down there, a couple of them. And so they said, well, you can't build here anymore unless you build everything up on stilts. So this is about 30 feet high. And so if you're going to build in the tsunami zone, you got to build high. And so that's what they do. You have your choice. Don't build or build it up on stilts. And as I mentioned, the watershed is really important as we have fires around the world. So forests burn and then there's less vegetation to keep sediment. So we have massive sediment plumes that push out the rivers and reform every single one of those estuaries on the Oregon shores. So you can't separate the fires in the mountains from the coastal wave dynamics. It's where the sediment comes from. Might take a year or two to get there, 5 years, 10 years. So this number of bailouts that the federal government is reimbursing. So they're up to 80% at Hurricane Sandy. So what's happening now is people are rebuilding in the flood zones, even though the flood zones are getting, they're expanding, if you will, and the municipalities are still giving permits. So need to change how permits are provided, especially if they're in flood zones or tsunami zones, because we can't just keep bailing out poor decisions. Unfortunately, the municipalities get all the fees for building and the increase in tax revenues, but the poor person that bought it after 10 or 15 years, or as we saw in New Orleans now, 2004, and then earlier this year, people lose their lives because of poor planning procedures. I'm getting real close to the end now. This is Walter Monk Way. Walter Monk turned 100 a couple of years ago. He's since passed away. Walter Monk was in one of the photographs early on in this presentation. During his 100th, during his centennial celebration, they dedicated this way. And he had many wise things during his lifetime that he uttered. And one of them was, he said, unless a concerted global effort to approach the human origins of climate change is initiated, unfortunately, Walter Monk Way, unlike me, Walter speaking, will never see its 100th birthday. It'll be underwater. So this is the Yellow Sea. This is Korea. These are sediment plumes. This is a satellite photograph. This is this amazing image. Here you see plumes of sediments. And so imagine if you're just at one little, if this was the coast of Oregon, you know, you have large tides actually in this portion of Korea. And if try to imagine and say, okay, what's happening at this little spot right here on the coast is very special. No, it's all connected. We're all connected. And I can't stress enough that you need to have a large understanding of what's happening from a scientific vantage point. And the most important thing is for individual citizens to become active in the coastal regions, to stop permitting and to not have sand mining in some areas, and have a sane approach to our coasts. So there we are. I'm not sure if you can see that. That says questions. All right, Philip.
Thanks very much, Kim. That was an amazing tour of our coasts and the things affecting them. I'll kick things off with a question.
Can you see that frame? Can you see that frame all right? Can you see all the way to the left of waves?
I can see it.
Can you see my cursor right there?
Yeah.
Yeah, okay, good. All right. Alrighty.
So
okay.
Talk a little bit about the effects of shoreline armoring and riprap. You know, how does that affect the shape of the beach?
Yeah, there was one slide there, I won't go all the way back to it, but where I showed a coastline that had a jetty. And so riprap is basically chunks of concrete and it has rebar in it. So random building debris thrown into the ocean. It protects that portion of the coast. But on the other side of it, so on the ends of it, so if here's the end, over on this side and over on this side, what happens is the waves wrap around it and it actually intensifies the wave action on the ends of that. So you get erosion. So if you're looking down here, you get erosion here and you get erosion here. That's exactly what happened when they built the North Jetty in Bayocean. They built the jetty up there. To the north of it, it was fine. They got sand deposition, but on the south side, it got erosion. So it's not a real sane approach to it unless you take a very large approach in the entire littoral cell, which can be tens of kilometers, tens of miles even.
I often wonder about that. There are places in the world that have massive shoreline armoring, as you say, that goes on for miles. I don't know, Galveston, Texas, to give you one example. There's a barrier there that I think it's 6 miles long or something. How long can those things last? I mean, if the ocean continues to rise relentlessly, can they stave it off forever by building higher and higher, or at some point will it be doomed?
Well, I mean, there are fortifications in areas that are, 20, 30 feet high, and they're well built. You see those usually to withstand armaments, battles and stuff, not to withstand the sea. But an unfortunate example is the Humboldt Bay jetties in Northern California. They've been building those things since, I think, the 1870s or something like that. And every few years they get destroyed again, or they have to add on to them. So even just in this, it's in Waves and Beaches. I think in 2017, they appropriated another $10 million to do not improvements, but repairs and augmentations to those jetties. So it's almost futile when you try and deal with large waves. The most important thing is you just build it in the right location. So you take advantage of what nature gives you with a headland, rather than trying to make your own headland, because they're expensive. Taxpayers probably don't want to pay that.
Well, over time, do the shoreline armoring then cause the beach to be eroded away because it's not being replenished from inland?
It depends. So if you have a, well, actually, I can maybe show here. So can you see my cursor there? Down in the
Yes.
bottom? Yeah. So if you were to build something here, right, is like make a little jetty out, or some riprap here, this would stay here. But this would be eroded, and this would be eroded. So here's a little bit of a headland, right? Maybe you should, pull it out from here and come all the way back to the next headland. But just to put a little portion in there is not adequate. I think they're building something in Nigeria. I think it's called the Great Wall of Lagos in Nigeria. It's over 5 miles long, and it's supposed to have, it's 10 square miles. It's supposed to have 250,000 people in population. So massive landfill. Now, I don't know how high above, they're not finished with it, but 10 square miles is a massive landfill operation. So hopefully somebody's looked in the wave climate. Otherwise, we're going to get a big storm and something won't be there anymore. So building something in this area will only give problems on either side of it. So you have to go from headland to headland, or cover the entire littoral cell.
Well, at the national level, how about the Netherlands? Can they somehow keep the ocean back, being below sea level with those massive structures that you showed us, or at some point is there nothing further they can do?
Well, the Delta project, I'm glad you bring that up, Philip. It is, in my mind, the most mature approach to coastal protection in the world by far. The Dutch are fabulous in coastal protection, but what they've done, they've codified it. They've actually entered into Dutch law that it is the responsibility of the government to do shore protection, and they do it sort of inversely what they do certainly in the US and most of the world. Rather than like with Hurricane Katrina, they simply said, oh, darn, 2004 inundated the city, and we need to have good pumps. We need to do the jetties and the fortifications along the river. And then they spent a few $1 billion doing it. Well, what the Dutch have done is said, look, we're going to say we want to build something so that if we have a 3 meter, I think it's 3 meter rise in sea level, that our fortifications can withstand that. And they do a cost benefit analysis. They say, okay, if it rises 3.5 meters, what's it going to cost us? Okay, well, maybe we should build it 3.5 meters. What's the probability that's going to reach 3.5 meters? Oh, 1 in a 2,000 year storm. Well, okay, we'll build it at 3.5 meters, and we'll spend a few billion euros, they use, so equivalent billions of dollars, to preclude massive losses. So the Dutch have done a fantastic job at protecting, with their Delta Works project, for protecting their shoreline, because they realize that the very existence, so it's an existential question for the Netherlands, well, for Holland, Netherlands, the whole country, and Holland, the section. So they've taken a national approach. Unfortunately, in the United States, we do not have a national approach. There is a bill that sort of stalled in US Congress for a national approach, national coastal marine policy, I think it's called. And that would be something to really support, because unless we have a national approach to how we're going to deal with sea level rise and climate change, because remember, sea level rise is only one symptom. If you get a change in the climate in the watershed, you can have a massive pulse of sediments coming out through the Mississippi or through the Columbia River or out through the Chesapeake Bay or breaking through barrier islands. So it's not just the sea level rise, it's the changing climate and the watershed dynamics with all that. We need to have that approach.
One of our board members I know had a question, and I don't see it in the Q&A, and perhaps she has been having trouble getting into it for some reason. So I know that the question was, as someone who I know lives on an estuary, she was wondering about the fate of spits. You know, you've talked about the Bayocean Spit, you know, but that wasn't, you know, sea level rise. That was a local influence of the jetties.
Human folly.
Yeah, exactly. But over time, with sea level rise and increased storm surges, what's likely to be the fate of spits like Bayocean or like the Netardt Spit or you know, name any other?
I tried to provide the understanding of the watershed, because a spit is basically view an estuary as a balance between the flow of sediments and the wave action on the coast. They strike an agreement. Okay, you're not going to just go straight out to sea with all these sediments, and well, we're not. And the tidal fluctuation says, okay, we're going to play games here, and the supply of sand is such that it can build a spit. Now, change anything in that dynamic, so the waves or the water coming down that watershed, you'll change the amount of sediment. On top of that, you have, well, let's, it's not something to really ignore, but just let's ignore sea level rise for a moment. A weather pattern change in the watershed can very easily blow through a spit and actually add to that spit. You can get massive deposition event too. You see that in the Elwha River Delta. It's built out probably 50 or 60 yards from where it was before. That's brand new land. It's in tribal land, so they have new land. So an oversupply of sediment you'd get with pulling out dams. You build the spit. You build perhaps even another barrier island. A deficit of sand or an increase in storm waves will cause that spit to diminish in size, or the waves can actually, large waves tend to move coastal sediments offshore, so into the bars rather than the berms. And a spit is basically something that stays above sea level most of the time. So you can have part of that spit grabbed by the ocean and moved offshore and form an offshore bar, but then you can have another storm come in. You can have the small waves come in during the summer and build up that berm again. So that dynamic, if it's gentle, will be seasonal. However, as I explained in Waves and Beaches, if you have equate it to being in a blender, so settings 1, 2, so high, low, medium, and high, or low, medium, high. The low setting in a blender, things just sort of move around a little bit. They'll come back to a steady state rest again. The medium level changes, small changes occur that don't reverse themselves. Whereas in the high setting, where you have lots of energy coming through the system, nothing is the same. It'll never return to that old state, at least within a lifetime, because too much energy has come into it. In the year 1900, off Galveston, there was a massive storm surge. I think it was the largest loss of life ever in the US due to natural phenomena, and basically washed away. I forget what the storm surge was. It was like 15 feet or 20 feet, washed away and cut through that barrier island, because Galveston's basically on a barrier island. So you can have episodic events that don't come back for 100 years or never come back. So there's no one answer to what's happening to the spit, because just take sea level rise. Well, okay, well, if you have a lot of rain up there, sea level can rise, but if you're getting more sediment, you're just going to form that bar again, a new bar.
Okay, we have a question. What are Kim's thoughts on desalination as a fresh water source for inland communities, in keeping with this webinar specific to the Oregon coast? And also it adds, thank you, kudos, by the way, on a fascinating presentation.
Thank you for listening. I almost put in a slide of desalinization. It's a slide from Malta. They've been doing it since the 1880s. At least there's still a structure from the 1880s. Now, Malta's got a different problem. It doesn't rain much there. So let's go to the listener's question in the Oregon coastline. So you can have saltwater intrusion into low-lying areas. So for instance, in the Tillamook embayment there, it's very low-lying. So let's say that the flow of water for some reason upstream was diminished. You would have more salt water coming in. So it wouldn't be flushed out as much, which means that the aquifer would slowly become more salty. With that, desalinization can occur. It's energy intensive. I just happen to know the number out of my head. It's about 4 kilowatt hours per cubic meter. So just call it like 3.5 kilowatt hours per cubic yard. That's 27 cubic feet. Excuse me for these units, acre feet and liters and fortnight. But call it 4 kilowatts per cubic yard. That energy has to come from somewhere. Now you can have a windmill turning that. Actually, that's the way that people have done it in the past for pumping water. So there's no reason why you can't create that pressure differential to run through the reverse osmosis, which is the method of choice currently for desalinization. In Saudi Arabia, they have massive plants. Down here, they have the largest one in the US is in Carlsbad, California, I think. And those use reverse osmosis. So there are methods of doing it. However, it's very expensive. It's probably 100 times more expensive, maybe even 1,000 times. I don't know the exact numbers. It depends. In Southern California, water is expensive. In the Northwest, some areas, it doesn't cost you anything. So when it's compared to natural sources of water, desalinization is very expensive and complex. So the best thing is protect the environment, make sure that the watershed is good, that the flow of things are correct. And overpopulation is an issue because as well as wells pump the fresh water out, I showed that saltwater intrusion slide, the water table, is supplanted by the salt water. So in the coastal region, it's probably not a really good idea unless you know the watershed's pretty stable upstream.
Okay, I think we got a question in the chat. Hi, where is it? Come back here. Hi, Kim. Excellent presentation. Will the wave energy devices, if and when implemented, affect the shoreline?
Not significantly. There's a section in Waves and Beaches in this new edition about wave energy. Waves are very energetic. So I won't go into details and numbers and all that, but as long as they're offshore, what they're doing is just diminishing a small portion of the wave energy. So I think the Bureau of Ocean Management, I think, estimates that there's enough wave energy along the US coast to supply all of our energy needs, but the mechanics of that are very difficult. If the wave, you can actually have a greatly beneficial thing. They've had breakwaters, and they've even had floating breakwaters. So you could actually extract the energy out of the waves to produce, let's say, electrical energy that would diminish the wave climate in an area where you actually want some sand deposition. So for instance, people have sunk ships offshore for diving purposes, and we've seen the decrease in waves along that on the leeward, so towards the earth and towards the land side. And with that diminishing waves, then you get some deposition of sand in that area. So you can see that with breakwaters when they do stuff like that. But wave energy extraction could be a method by which you actually diminish the waves, which you might want to do. So if you place them in the right place where you have big waves, you can not only extract energy from it, but you can also do a little shore protection, which would change coastal dynamics, but not massively if it's a mile or two offshore.
Okay, thank you. I think we have a raised hand. I'm 100% sure how to open this. I'm going to try. Allison, are you there? Unmute yourself.
Yes, can you hear me?
Yes, now I hear you.
Yes.
Okay, great. Kim, I had a question about Sand Lake area of Tillamook County, just here on the other side of Cape Lookout from me. And I wondered if you could talk about that.
I'm not familiar with the geomorphology of that area. So Cape Meares, you say?
No,
Which-
it's called Sand Lake. It's south of Cape Lookout. It's a sort of a sand dune preservation area.
Oh, is that? Oh, I think I know. There's a lot of inland sand dunes.
Yes.
Yeah. So what's your question?
Well, there's a great deal of sand there. It seems to go back, a mile or two, but there's also an odd island with water coming in on either side of it from the ocean. I just wondered about that, but if you don't know it, that's cool.
Yeah, on the Oregon coastline, there are a lot of, I think they're basaltic, not domes, but leftover hard material, and you'll see those along the coast. That's really hard geology, and in between, it's all been eroded. So what you see there, the sand blowing inland, is the earth, the geology that can be eroded easily by waves, and the stuff sticking up, those are going to take a long while to erode because they're basaltic, they're super hard stone. So I don't know if that's answering your question or not, but that wind-blown stuff will go, as long as there's an oversupply of sand on the beach and the wind keeps blowing, it'll keep building up the, I showed just a coastal picture of the dunes in Namibia, in just north of South Africa, on the west coast of Africa. It goes in 100 miles.
Wow.
It just keeps blowing in. So as long as there's an oversupply of sand from the land and the wind keeps blowing, it'll just keep blowing it up. It'll just keep going.
Yeah. Thank you. Thank you.
I was intending to credit Rena Olson, our communications manager, for actually running this from behind the scenes. I see a note that said that she wanted to answer this question live. Was that you, Rena? Did you want to chime in here?
No, but Christine does have a question.
Oh.
If we can have her unmute and ask it.
Okay. Christine, are
Okay.
you on?
Hello?
You need to unmute.
I did not, my question was answered, but great presentation, and I'm very enthusiastic about what.
Oh, we lost her.
You're muted.
Yeah, I was just saying my question was answered, and I'm just excited about what to do next with all this information, especially wave energy.
Well, I hope my talk was not too much Debbie Downer, as they say, because there's lots of things that can be done. Unfortunately, in the little amount of time, I wanted to provide more an understanding of waves and wave action and a little bit of the dynamics rather than what can be done. Now, in Waves and Beaches, I do talk about, there's a section in the appendix, and it has a bunch of coastal management plans from around the world. So if you go to the appendix of the 3rd edition of Waves and Beaches, you'll see a whole bunch of coastal management plans. So there's thousands of pages referenced there, actually, that will provide detailed information about what different municipalities and states Also, countries are doing around the world. The Australians, Isle of Man, Isle of Wight, state of Texas. Unfortunately, we don't have a national policy. Waves and Beaches also, well, the book Waves and Beaches has over 150 references in it also. So you can dig really deep into what is being done and what can be done. But it's just too long of a topic. It's almost like a whole monthly lecture to go into that detail.
Okay, I think we've exhausted our questions, and this seems like a good stopping place. So thanks very much, Kim. This has been, again, an amazing tour of the world's coasts and the things affecting them. And as Christine said, a lot to think about. So thank you for being with us. I think we'll all be reading Waves and Beaches now. And thanks to everyone for attending. Again, thanks to Rena for setting this up. And I'll just note that a week from now, on October 13th, Dr. Christy Croker from University of California at Santa Cruz, my fellow banana slug, will be speaking on our changing oceans and the changes actually taking place in the water, such as acidification. So catch us with that in a week. And for now, good night, everyone. Again, thanks for joining.
And I'd like to thank Jesse Jones for facilitating all this. Unfortunately, she couldn't be with us, right? Yeah. Okay.